Okay, so here's the sort of physics review. I save sort of because you can always go back and look at the other reviews and know what we did in the other tests. I'm not really going to talk about it, except just to give you a general idea of what you should know for the exam, especially since about half the class has just taken the retake of test number 4. So that should, if you study well for that, you understand what's going on, then it shouldn't be a big problem. Okay, so we basically have one-dimensional motion and specifically constant acceleration type problems. So you can go back and look at test number 1, where we had constant acceleration. And there are the 4 equations, which you should know by now. People who didn't know it aren't in the class anymore. So everybody who's there should know what's going on. And the basic idea is of the 5 variables, the variables being B, B0, T, delta X, and acceleration. Those 5 variables, I give you 3 of them, and you calculate 2 of the other ones using the 4 equations. And we try to, avoid equation number 3 somewhat if we're trying to solve for time, because you have to solve the quadratic equation. So it's sometimes easier to solve for velocity from this equation, actually solve for acceleration from this equation, actually velocity from this equation, and then you can avoid using that one. So it's not that I'm saying you can't use it, but you know what I'm talking about. Okay, so there'll be a problem or problems associated with one-dimensional motion. Okay, then we have projectile motion. So the only thing there is what we do is if we have a initial velocity that's has both an x and a y component, we break that up into the initial component in the x direction and the initial velocity component in the y direction, and we have this angle with respect to the horizontal, and therefore just from trigonometry we know that v0y is equal to v sub v0y. What I'm going to do here is, you got to be a little careful on the sign. So I'm going to say the magnitude of v0. So it's the value, the length of that vector times the sine of theta. And then you've got a plus or minus in here. And in this case, it's positive. So you have to look at your vector in your drawing to know whether it's positive or negative. In the same way, v0x is equal to plus or minus. That's the magnitude of the vector times cosine of theta. So if this were pointing down like in this direction, then v0y would be negative and v0x would be positive. Likewise, when you get to the end of your, so what happens is you break it up into these components, and then you have 2 directions. You have the x direction, which because of the way we define x and y like this, in the x direction, v sub x is just the initial velocity. So the x component of the velocity doesn't change. And in the y direction, we have constant acceleration. So this is constant acceleration. Here we have constant velocity. It's also constant acceleration, but it's 0. So this is constant velocity. It's constant acceleration. So there's only one equation when you have constant velocity, and it's velocity is constant. And then you have your 4 equations here. And the thing that keeps these things together is time. That's the one variable that links the x, y directions. So, if you look back at the problem on, I guess it's test number 2, I gave you this velocity here, and I gave you an angle. So you calculated v0x and v0y, and then you could use the y direction to figure out how long the object was in the air till it hit the ground. So you get the time from that, and then you could use the time. So the displacement in the x direction, or in this direction, is just the initial velocity times time. So that's our one equation that relates displacement with velocity, whereas over here we've got the 4 equations that relate things when you have constant acceleration. So anyway, I think most people know how to do that. So you go back and look at test number 2 review, and you can look at an example. Okay, so then we came to chapter 4, which is Newton's second law. So actually, I think there are 2 problems that involve Newton's second law in terms of linear systems. This is an easier one, a harder one. So, of course, I can't tell you what they are, but, Newton's second law, there's actually 2 cases. We've got the equilibrium case, and equilibrium just means that A is equal to 0. The acceleration is 0. Usually that also means B is equal to 0, but it doesn't have to be. But most of the time, things we consider, things are not moving, not accelerating. So you have the sum of the forces in the x direction equals 0, the sum of the forces in the y direction equals 0. This is chapter 4 stuff, so we haven't introduced torques yet. And so, the only kind of problem really can do that, have this kind of system, is where you have 3 forces that are acting through, or 3 or more forces that are acting through a common point. So if you remember the problem we had there, is you had a mass hanging from a rope, and then 2 ropes were holding it up, and they all connected at this one point. And that's because now that you know more, now you know about torques, there's no torques made from a case where all the forces go through a single point, because there's no momentum. So, that was a matter of breaking this up into 2 components, and then using one equation. Sometimes you have to use substitution. Anyway, you can look at that. That's one of the problems was on the test. And then you have the non-equilibrium conditions. So under those cases, you have the sum of the forces equals the mass times the acceleration in the y direction, and then you've got sum of the forces in the y direction, x direction here, and then this. But if you choose your coordinate systems correctly, you can usually make it so that this one is 0. So if you choose the appropriate coordinate system, this is 0. So, the simplest case is something sliding on a horizontal surface. So I think this is one of the problems we had, where it's moving at a certain velocity, and then you've got the friction force pushing backwards, slows it down, and you figure out how long it takes to slow down. So that's one case. Then you have the more complicated case where you have an inclined plane, where you've got to break up your, in this case, choosing coordinate system appropriately. So if you choose your coordinate systems such that the x direction is along the plane and the y direction is perpendicular to the plane, in this case, there is no movement perpendicular to the plane, so this applies. So in this case, for this any block that's being pulled up or pushed in, sliding down there, sum of the forces in the y direction equals 0, and the sum of the forces in the x direction equals the mass times acceleration. So, we have the more complicated case. You have a rope attached to a frictionless pulley, and then it hangs down like this. Then you've got two equations. So if this mass is sufficient so the weight of this allows you to pull this thing up, it's going to go one way. If this mass is sufficiently larger than this, then it's going to go the other direction. So again, be prepared for anything relative to things moving this way, things sliding up like this. So there will be friction on here. If you go back to chapter 4, as far as the videos are concerned, you'll see all those different combinations of things happening, and you do free body diagrams, and then you sum the forces in for the two bodies. In this case, this example here. So you'd have some of the forces in the x direction are going to be equal to the tension pulling like this on the cable, and then you're going to have friction force pushing down, and you're going to have the weight, which you break up into your two components, and then you're going to have this one where you do a separate sum of the forces on this object, and the thing that links them is there's really two things that link them, is that the acceleration of these two objects are going to be the same. The linear acceleration is going to be the same. And also, because the pulley is frictionless and massless, these two tensions are going to be the same. So we actually connect these two free body diagrams and the corresponding equations by those two properties. Again, you can go back and look at the review, or the review might have told you to look at one of the videos. So there's also, the third case, which we haven't looked at. So you got things moving on the horizontal surface. You've got things moving on an inclined surface. You could also have something falling, so free fall, which is pretty boring if nothing's going on. But say you have a mass, this mass, and it's going to fall. If you actually had some kind of force that's pushing up, some force of due to air friction, that might be a fixed force. That would be another case. In this case, you'd only have to worry about things in the y direction. You'd have the weight pulling down. You'd have the friction force due to air pushing up, and then you would set that equal to the mass times the acceleration. So you can solve the acceleration by taking the difference between these two forces. This one depends upon the mass. This one may be given to you, and you could solve that kind of problem too. Okay, you guys did pretty good on chapter 5, which are energy. So there will be an energy problem on there. So remember, what we did is we wrote down that the non-conservative work was equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. And again, this is one-dimensional stuff, so we're not dealing with rotating things at this point. And you can simplify these things depending upon what's happening. If there's no elevation change, you can get rid of this. So there's spring involved, you can get rid of that. If the velocity at the beginning and the end is the same, maybe 0, then you can get rid of that. If there's no friction, then you can get rid of that. So typically, you can, most of the time, you can get rid of 2 out of the 4. Now, it doesn't mean that you can't have a problem with that, which would have all 4. It would be kind of complicated and not something I would put on the test. So the first step is you're going to do is you're going to write this out, get rid of the terms that don't apply for the particular problem. And So this is, I'm just going to show you what a problem would be if I did include everything. How would I have a problem? Well, if I had an inclined plane with an object, don't write this down, just pay attention. So, I have some kind of object. So it's going to slide down. There's going to be some elevation change. So there's going to be some change in gravitational potential energy. It runs into this spring like this. And as it's going down, it has friction. So what will happen, and also we'll give it some initial velocity. So instead of just starting at the start, rest, compressing the spring all the way, so it's at rest. If I gave this some initial velocity, 4 meters per second, I gave you the distance before it hit the spring, and then the spring constant. So there are cases where you have to consider all 4 things, but you're not going to have to do it this time. So remember, the non-conservative work is equal to negative friction force. Well, for most cases, it's equal to the work, which is force acting through a distance. So you're going to have negative because it's non-conservative work is going to be negative work. You have the friction force, and you have some distance that it slides. So that's typically what it is. And, of course, the friction force is equal to the coefficient of friction, kinetic coefficient of friction, because it's moving, times the molar force. Anyway, you can look at the problem that we did for that particular test. Just to review what we did. So that was energy. Then we had momentum. So we had 3 kinds of collisions that we looked at. Actually, 4 kinds of collisions. There was inelastic. And for all of these, conservation of momentum is the same. It starts out as the same. Conservation of momentum says you have some object 1 moving at some initial velocity, and then you have some object 2 moving at some initial velocity. The product of these 2, mass times velocity, is the momentum. In this case, I'm just having things move along one direction. So momentum is a vector, but in this case, I'm making it into a scalar problem by I have to put like a subscript x or something like that. And then you've got the momentum after the collision of the 2 objects. So for the inelastic collision, the key thing is that the final velocities are the same. They stick together. So again, we had this problem where we had a bullet shot into a block of wood, and of course, once the bullet's in the wood, they're going to move at the same speed. So that's inelastic. You had elastic, but not perfectly elastic. In that case, you have to use the full equation, because elastic means that they're going to bounce off each other. But you may not conserve energy. You may not conserve kinetic energy. So in this kind of problem, you have to be given one additional piece of information to be able to solve. So if I had a problem like this, I'd have to probably give you the 2 masses plus 3 out of the 4 velocities. And then you could solve for whichever velocity it didn't do. Okay, so there's elastic, and then there's perfectly elastic. And what that is doing is it's telling you that during the collision that all the energy is stored in a spring, a perfect spring, or in a magnetic field. And in that case, you have the change in kinetic energy equals 0 joules between before and after the collision. So in that case, you've got the conservation of energy in its simplified form for just 2 objects, the perfectly elastic collision. And I'm afraid of writing it down because I don't remember the signs, so you can look that up in your notes. And then there was the explosive collision, which is really kind of an uncollision. So that's, this is kind of like guns or somebody shooting something, so the bullet comes out one way and you get a recoil. You've got, space astronauts throwing wrenches. What happens there is the initial momentum, which is equal to the final momentum, they're equal to 0. Now, initially the momentum is 0 because velocities are 0. So basically this side is 0 just because no velocity. V equals, V initial equals 0 for both cases. For the final, what happens is you got momentum going one direction and momentum going the other direction. So you got a minus part and a plus part, and these things have to be the mass times the velocity have to be the same. Okay, so that's all I'm going to say about that. Then you've got rotating stuff, rotating systems. So just go ahead and review what you reviewed for the last test. So the main things you need to be able to handle is a some kind of pulley that has some torque applied. Most of the cases, as you know, have one or two forces acting on them because of weights that are hanging. So I've asked you to basically learn a few specific examples that cover all the concepts instead of trying to have you be able to do all kinds of less complicated problems. So that's my philosophy, just to give you a feel for the complex nature of problems when you involve more than one or two bodies. So, you have the kinematics part, which is just the 5 variables and the 4 equations, just like we do for linear systems. For rotating systems, you've got this where things are actually happening, and these masses are treated exactly the same as they would be in a Chapter 4 kind of problem. You've got this extra complexity when the pulley has some mass and some moment of inertia, and we get one additional equation, which is the sum of the torques is equal to the moment of inertia times the angular acceleration. We also then have that the linear and angular properties are related by the this equation. And so if you know the linear acceleration of these masses, then you can solve for alpha, or if you know alpha, which is what the angular acceleration is, you can calculate the linear acceleration. So these are the 2 new things that you have involved in rotating systems. And we also have the equilibrium case, which we've dealt with these beams. If you go back to what we talked about equilibrium in Chapter 4, we had, where was that? Right here. Everything was applied at a point in space, whereas once we have taken into account rotation, then we can deal with beams. And so again, make sure you know how to do a beam problem. Hopefully you've got it right the first time, and you also you're going to get it right the second time when you take your test 4 retake. Then we also have conservation of angular momentum. Again, look at your review for test 4. And then the final thing is Chapter 9. So what do I want you to know for Chapter 9? So I'm not going to ask you. Okay, so here we go. And it's not going to be everything that I'm listing here, but I do want you to review it. So the main things we talked about were deformation of solids. So we did quite a few of these examples in class. So you have that the stress, you can look up all these details. You know, the stress is equal to Young's modulus times the strain, where the stress is equal to force divided by the area. So if you have an object like a rod, and you apply a force to both sides, it has to be equal force because otherwise it would move in one direction. So the forces are the same. If you look at a cross section, if you don't cut it open, but you just imagine you have a cross section here. The stress is the force divided by the area. You can imagine that as this area gets smaller, that you're going to put more stress on the molecules and the matrix structure of the object here. So the higher this number, the more likely this rod is going to fail. So that's stress. Force. Stress is newtons per meter squared. Force is newtons. Area is meters squared. Then you have strain. Strain is the change in the length divided by the length. So, if this thing is initially 2 meters long and you apply a force, you get a deflection. If the object is twice the length, then you're going to get twice the stretch. So that's what this is. It's the change in length divided by the original length of the object. This is usually a very small number, except for things like rubber. So things like steel, copper, glass, concrete, pretty much anything except for rubber. This strain can be a very small value. And then E is that's called Young's modulus. And that's the constant that relates the two. So just look through the examples that we did in class. Then we had pressure variation in a liquid. So this could be, a liquid is either, actually, I guess it should be a fluid, because a liquid could be, I want to make sure you know this could be either liquid or gas. And what we did, if you remember, is we looked at a height of column of fluid, which had a height here. And because of the weight of the fluid in this column, the pressure at the bottom is higher than the pressure at the top. And everybody, you know that because if you go into water, you start to hurt because of the pressure increase. So the pressure increases. And it happens more rapidly in liquids because the density is much higher. In air, you have the same difference. You have the same effect, but it has to be a large height of air to get significant pressure. But in any case, let's say the pressure on the top we'll call P0. And we'll call the pressure on the bottom equal to P. And the pressures are the force applied per unit area in that fluid. So the pressure at any depth is equal to the pressure at the top plus the density of the fluid times G times the height. So I could give you a problem where, ask you what is the pressure at the bottom of the pool, what's the pressure at the bottom of the ocean, assuming density is constant. I'd have to give you the density. You should know what G is. H, I'd have to give you something like that, and then I could give you the pressure. And the units for pressure are newtons per meter squared, which for pressure we call them pascals. And if you remember, atmospheric pressure, which is the pressure that we experience here on Earth, is approximately 100,000 pascals. I think it's 100,000, I'm going to say 300 pascals, or 101.3 kilopascals, or newtons per meter squared. Okay. Then we had buoyancy. And the big thing that you guys are not supposed to forget is when something is floating, the total weight is equal to the buoyant force. So let's say we have some fluid here, and we have an object that's floating in the water. And let's put, a big pile of gold or something on here. Now, if I take the gold off of here, what's going to happen is it's just going to go like that. And under these conditions, the amount of volume that this thing displaces is going to be equal to, well, the weight of the fluid displaced, meaning that the part of the water that's displaced by this rectangle is going to, the weight of that is going to be equal to the weight of the actual piece of wood. Now, if I take this piece of gold on here, then what's going to happen is thing's going to sink. That's not going to sink. It's going to go lower in here. And so because I have this extra weight, this thing is going to have to move down to displace more of the liquid. And you can figure out how much this thing is underwater by finding out how much weight we have here, which is the mass of each thing times acceleration due to gravity. And then you could figure if this thing has a consistent profile as it goes down, you just take the area profile multiplied by this height, and you can figure out how much volume is displaced. So remember, the buoyant force is equal to the weight of the fluid displaced, which is the density of the liquid, in this case, whatever we're displacing, times the acceleration due to gravity, times the volume displaced. Okay, that's displaced. Okay. So, if this thing's floating, then the buoyant force has to be equal to the sum of the weight of this floaty part and the weight of the non-floaty part. If I took this gold, it would go sink. But as long as the weight of this thing is not large enough, not too large, then it's going to, it's going to go down into the water, but it's not going to sink. So if you knew this is your weight, and you know the liquid is water, that's 100,000 kilograms per meter cubed, that's 9 meters per second squared, you can calculate the volume displaced. And once you know the volume displaced, you can figure out how much height the thing goes down. So that's buoyancy. And then we also talked about, the last thing we talked about was Bernoulli's equation. And this was for everything we've done so far is basically what we call fluid statics. Things are at equilibrium, whether it's because fluid is just sitting in the tank and we want to know how much the pressure varies with height, or it's something that's floating and sitting there and not bobbing up down. The final one is Bernoulli's equation, and this is for things that are flowing. And we looked at a couple of examples there, but Bernoulli's equation says that the pressure at some point 1, some position 1 in the fluid, plus, what do we got next? We got 1/2 rho V1 squared plus rho GH1. And we're assuming the density of the fluid is constant. That's going to be equal to P2 plus 1/2 rho V2 squared plus rho GH2. Remember, pressure in pascals, density kilograms per meter cubed, velocity meters per second, density kilograms per meter cubed, G meters per second squared, 9.8, height meters. Okay, so those are the units for all those parts. And so we looked at a couple of cases. We looked at the case of a channel where it contracted, but it was the same height. So just like we did with conservation of energy, we try to simplify this by getting rid of terms that are not applicable. So if there's no height change, we can get rid of those two. And you can see the pressure change is going to be proportional to the velocity, square of the velocity change. We did the tank where the stuff squirted out the bottom. In that case, the V1 was 0 because we had the big surface. P1, if we do the surface, then P1 is the atmospheric pressure. Actually, P2 is atmospheric pressure if we chose them directly. So the height of the fluid can be related to the velocity change, especially since this one's 0. So just look at those two examples. I'm sure they're in your book if you need to find something. So that's pretty much it. I think I've got 7 problems on the final. I can't cover everything, but I'm expecting you. I'm not going to, I think you should be okay.